then we'll jump into the lectures. Lithography. So this is what we are studying now, chapter 2. I didn't put up because we're going to continue with lithography for 4 lectures. Lithography 1, 2, 3, processes, materials, then optics related to lithography. So today I wanted to discuss the basic idea of lithography. So have you guys seen a liner? You guys seen a liner? Do you know what's an aligner? So before we do the exposure, we have you seen the photoresist dispensing chuck, the equipment where we do that, we apply the resist? Have you seen that? Those who have not seen how we apply photoresist. So everybody knows how we do that. You haven't seen how we apply photoresist. So it's essentially a chuck where a platform that we use to dispense the photoresist. So this is a small video. I hope this works. Oh, this is upside down. This is some promotional material, but it gives the idea that we dispense the resist and we rotate the wafer, which is being held on a chuck with vacuum. So that chuck has grooves in it through which we apply vacuum from the center and dispense resist. And so this is talking about something else, but the focus is here that you apply resist and you rotate the wafer, and that results into the resist being spread out evenly on the surface. And there's this guy which is probably upside down. Gives you the, so here is the resist. Oh, here's the wafer. This is the wafer. It came out to be upside down, but so we are applying manually resist through a pipette, and while it's rotating, it spreads it evenly on the surface. So you see that coloration, the colors changing on the, is it visible? So you see this will be dispensed from here. This is the wafer which is rotating. There's a spindle here. Now once you see these drops coming, this is spreading. Once it spreads, you see the color change, which is essentially it's drying off. So you see the color changes from here over the wafer. So it's rotating at, generally we rotate at 4,000 RPM. So this is how we apply photoresist, and then we take it to the exposure system. Right, so talk about materials, photoresist types, and what's the process flow. So that's the major fundamental step where we to translate the design of integrated circuit onto the final physical shape. So over decades we have been pushing the feature size down, and so we are pushing also the photolithography system, mainly the wavelength of the light that is used. So G-line liners, I-line, and onward. So G-line and I-line are just named for the exposure system that use 436 nanometer wavelength and 365 nanometer wavelength of light source. So the simple relation with lambda, which we saw in introductory slides, with what did lambda dictate it? And wavelength had direct effect on what? Frequency, of course, wavelength and frequency are just
minimum resolvable feature.
Minimum resolvable feature or
Critical dimension.
critical dimension. So minimum feature size is accurate word, because resolvable feature come, then we have to consider the pitch also, which is more comprehensive term. But lambda has direct relation to minimum feature size, which we denoted as W min there. I didn't ask any question from there specifically, because it goes with photolithography. So probably next time we'll have much more on that. So we push down the wavelength and we can make smaller features, right? So which is visible that we're pushing the feature size down. So respectively, the wavelength or used in those equipment. So the whole technology is scaling down. So wavelength is the major factor. Now when we push down the wavelength, not necessarily it's good, because our depth of focus is also reducing. Remember, we saw depth of focus as well. What was depth of focus?
How deep can your focus spot go in the resist?
How deep your focus spot can go in the resist. So more precisely, what would be the depth, right? In what would be the Z distance in which your feature stays focused within allowable limits, right? Of course, we know that it will be precisely in focus only at one depth, right? But there's allowable limits that we can live with. And when we say focus, when a light is focused at certain depth or certain point in space, that point gets the maximum energy focused at that point, right? Anything beyond and below would be where the energy will not be transferred maximum, right? So depth of focus, like in photography, is where we focus on one image, but the rest of things can go out of focus. And it makes very nice artistic photography. But when we are imaging a big landscape, we don't want to do that. We want to have everything in focus. So depth of focus depends on what is our application with. But in this case, we want depth of focus to be a smaller distance or a larger distance. Why is that?
You want to expose the whole thickness of the resist.
And of course, we want to expose the whole thickness of resist. We can just make a resist thin for that matter.
We might not want it.
Okay, it's one possible solution. What I'm driving at is trying to have a larger depth of focus is not only driven by the thickness of resist, because we can always come up with a new chemical which is thinner, but
There might be several layers.
there are layers. There is topography on the surface of the chip, right? So topography means you have now made different levels of devices which result into the surface which is not planar, which has local planarization. Maybe you can get local planarization, but there are different levels now which are at different height, right? So not just the minimum feature size, depth of focus is also an important factor, and both depend on lambda. We want to push lambda or wavelength down to have minimum feature size, but that also results into depth of focus reducing. So it's, what do we do there? We'll see. And maybe this, I know for once this is already a topic of one student's paper, how new technique we can do to push those limits back. not changing wavelength, but doing something else. We'll look at that. So, again, overall, we use CAD systems to design layout. We simulate our circuit. We check that it fits all the design rules, because on computer it will work, but now once you translate into multi-layer masks, we have to make sure that we get all the features down on the wafer, doing the actual processes. And once we get that, we define set of masks from that, which are directly written, because mask is that contains the opaque and transparent regions, which will be ultimately used to shine on the surface of the wafer in resist, right? So they can have very fine dimensions in there of the features that we ultimately want to make, and then we expose our wafer. So there are few ways how we do that. We can, in this case, what we see is a big mass and a smaller die. What do we call that when we are doing photocopying? What do we call that?
Reduction.
Reduction, microcopy, right? We make a microcopy. So especially when you guys are allowed cheat sheet, you want to cram the whole book on one page, right? So that's now intuition, or our knowledge tells us when we make a microcopy of something, are results better than the original or worse?
Better.
If you want to enlarge a copy, is result better than the original or worse? Mostly it's not as good as a microcopy would look like, right? Because we now have some resolution and we make an image which is high resolution, right? We compact those pixels, bright and dark areas, into smaller regions. Similar is the case when we, so this is one way of how we do that. We get a microcopy of design on our wafer. We'll see what do we call that and how does it benefit us. But generally the idea, the whole process of lithography is we clean the wafer, we deposit the protection layer, whatever hard layer we're going to use to transfer the pattern. It can be silicon dioxide, silicon nitride metal, right? Whatever. We coat it with resist. Then we do soft bake. Why do we do soft bake? Why do we call it soft bake? Two questions. Why do we do soft bake? I have just put my resist out. Why I want to heat it?
Adhesion.
Adhesion? Anything else? I want to get rid of all the solvents that were there, which were giving the resist its liquid quality, right? Because I want it to be hard now. So we want to adhere it, and we want to get rid of solvents. We call it soft bake because it's done at relatively low temperature. Low temperature is 90 degrees, because hard bake we do at 100 degrees. So slightly less temperature than what we're going to do afterwards. So do soft bake. If it's first mask, do we do alignment with first mask as well? I'm using first mask. There is nothing on the wafer yet, right? Do I have to do alignment?
Still want to align it with the wafer so that you're not exposing it off the wafer.
Of course. So yeah, of course, it is very logical that we have to have wafer somewhere below that mask, right? But precisely when the equipment will do that for you, you don't have to worry about that. But when we say alignment, that means do you want to adjust mask in X, Y, and theta? Do we want to do that? There is always a flat on the wafer, right? You know that. So we want to put flat in some general direction. So next time when we are putting it down, we can do this macro scale alignment, that we put the flat in same direction, right? And then we'll look for our alignment mark. So yes, even when you're doing first exposure, we align the wafer, and there is on that wafer chuck, again, it's wafer chuck or wafer holder in a mask aligner. There are some very small notches or small grooves, not grooves, raised, what you call, pillars. We use those to put the flat in certain direction. Mostly flat is towards me, right? So the next time when I'm putting them, I know generally that flat should be again towards me, and then I'll do my micro scale alignment where I'll match the patterns. But yes, we do alignment with the first one as well. We expose the wafer. Now, when we do exposure of a negative, or what we call that roll films in those old cameras, what were the factors we adjusted before we captured the image? Focus, right? So we have to make sure the image is making a very sharp contours. We have to do focus. Here we don't have to worry about focus because generally the distance separation between the mask and the wafer is very well defined, right? But yes, we will have to do focus if there are multiple structures being done. What else do we worry about?
Shutter speed.
Shutter speed, right? What does shutter speed define?
The duration of
The duration of exposure. And what is the third thing? Aperture. How big of an aperture to use, right? So if you now think about it, by shutter speed and shutter aperture size, we are basically controlling what? Light intensity, right? How much light for how long? And that is in terms of charge. What do we call that? We looked at in ion gradation. Dose. We want to control dose. So when we do exposure, we have to know the dose we want to use. What would define dose? In this case, of course, dose. I know how long I have to expose and what energy should reach the wafer. What would define the dose? There's no aperture here. We are just setting the time, and we know how much energy is going to get there. What would define for how long I have to expose this wavelength and this energy? What would be
chemistry?
The chemistry of
the photoresist.
Of resist.
For each one.
Photoresist will define, the chemistry of photoresist will define how much dose. Not just chemistry of photoresist, physics of photoresist as well. How thick of photoresist are you using? Because you have to expose the whole thickness of resist. Right? So if you are using thin photoresist, same photoresist, one case thinner layer, one case thicker layer, which one would need more dose? This guy. That's why you lose your train of. So use same resist. In one case I use thin layer, the other case I use thick layer. Which one would need more dose? Thick one, right? So the light can travel all the way down and it change the whole chemical nature of the resist, whatever needs to be done. So resist properties would define the dose. So before we do exposure, we need to know, of course, we can't change the light source on a given aligner. We will know it's I line or G line or 193 or whatever aligner is that, so we know the wavelength. What we can know, we can figure out is put some equipment there and figure out how much energy reaches to the level of the wafer. Right? Why should that change for a given system? Why should, so I'm using a lamp, right? So there's no dimmer for that lamp. We switch it on and it gives out some energy. Why would that amount of energy that it gives out would change? Because it's a lamp. It's just a bulb, right?
Oh, it degrades over time?
It decreases over time. So aging would result the energy that reaches, through naked eye you won't be able to see the change. But for resist, that's a chemical reaction that has to occur. So we have to know how much energy reaches It's generally millijoules per centimeter square. And then that will tell me how long do I have to expose. So there will be exposure time that I will use for exposing my certain photoresist that I've applied on my wafer, and I have certain thickness, so I would know how long I have to expose. I cannot control the energy that reaches the wafer. Yeah, I can replace the bulb, right? But I have to figure out how much energy is reaching there at the wafer level, and then I adjust my time. So basically I'm controlling the dose that it gets exposed. So that's in the exposure. Once I get the exposure done, we develop it. So developing is putting it into a chemical that would react with the exposed part if it was negative resist or positive resist. Do I have hints there? No, I don't. That's good. So we'll come back again. So I'll develop, basically I'll get rid of resist from some parts, depending on positive or negative. Either case we'll see which one goes away. And I have some pattern now. What do I do with that pattern? If I had silicon dioxide beneath, I'll just dip it in BHF, get rid of silicon dioxide. So I have now pattern transferred into this hard film. I can get rid of my resist now, right? Maybe I have to keep resist on because I may be doing some further processing. Maybe I'm putting metal there in that region opened up by oxide. Maybe I'm putting metal there. So I may want to hold on to my resist. What we do is hard bake. Hard bake is same furnace, longer time, higher temperature. Why do we do hard bake? So first bake was to get rid of solvents. The second bake is to
vitrify the resistance.
So to better define the resistance.
Vitrify.
Vitrify.
Or do we not want to ever get there? You know, turn it into glass. Turn it into
classify the resist, right? To make it really hard that it doesn't reflow, doesn't change. In some cases, we want to heal resist also. In some places where we might have some defects in the resist, which will be healed by hard way. And then, before you do oxide etch, we do hard bake before that. So the chemical doesn't get rid of, doesn't attack the resist itself. So we classify it. Then we can remove resist or keep on. For if we are doing metallization, we may want to keep on. Next we'll see what is that metallization process. So at this point we can do the process and go back to this step. This or this, whatever is the case. Why? Because we start with the wafer. First we may have an insulator to make our implanted shallow junctions or diffusion, whatever the case may be. And then we have to put metals on top. We have to then get rid of the resist and align our second layer, and maybe now we have to open these windows for connections to the source and drain, right? So this is just an overview that this would be made by mask 1, this would be made by mask 2. At the end of the day, we want something like this, which has source, drain and gate, right? So multiple steps of masking will happen. Multiple steps of lithography will occur for that. So it is not only used to define pattern, it's also used to protect the underlying layer, right? So in whatever case we do, it's an optically sensitive resist. It's exposed to light through a mask. A pattern is formed. That pattern is used as protective layer in implant or etch step or deposition or whatever process is coming up. Or maybe metallization is also metallization, right? Yes. So positive and negative. If positive, what is the positive attitude? You get exposed, leave, right? You lose the game, just leave like a gentleman or a lady. In negative resist, you become stubborn. You get exposed and you're stubborn now. You're staying, right? Easy to remember. Positive resist, you get exposed, you leave. So positive resist gets, if this part gets exposed, this part gets removed. In negative resist, if so this T shape is getting exposed and this is this is the opaque region. So this T shape is opaque region that gets washed away. Right? The one which is exposed, which is everything else, that stays. In this case, that goes. Right? Any confusion on resist type, positive resist or negative resist? Unless I specifically say what type of resist we will be considering always? Positive. Right? So positive will be wherever it gets exposed, that gets dissolved. It has material advantages for high resolution as well as it is less carcinogenic. The negative resist were carcinogenic. How do we print the pattern? One is called contact printing, which we most oftenly we do in labs. Contact printing or proximity printing, where a mask is in contact with the wafer. Right? And in this case, it's just a few microns away from the wafer. But what industry uses is called projection lithography. What it does is projects the image through lenses onto a wafer. What do you see to be major difference between these two? In terms of the size, the feature size on the mask and produced on the wafer. What is the relative difference in size between two cases, on left and right? In contact printing, it's the same size. It's what you see is what you get. So you make your critical dimension is exactly what's going to get translated. But in projection lithography, it can be scaled down. So your actual feature can be larger than what you are going to get by projecting it, by what do you call it, making macro copy of the design, right? So we can scale down 10 times. How does that translate to ease of making mask? If I want to make a, say, 1 micron line, which mask is easier to make? This guy. So I can make a 10 micron line and get 1 micron projected, right? So making a bigger feature is a lot easier than trying to make that 1 micron line in the mask, right? In contact printing. But in contact printing, I can make, the equipment is simple for contact printing. You don't need these optics to adjust your size and zoom in and focus and all that, right? So you make a mask and you just plug it in and expose, you're done, right? So there are trade-offs, but industry uses projection lithography. Now, if I do this, then what do you think? The rest of my wafer is going wasted. I'm just exposing on a very small part of the wafer. What do I do to use the whole thing? It's called stepper. We step, repeat. So it's a step and repeat process then. So you have the whole wafer, you expose, take a step, expose, take a step. So the system is called a stepper, or the whole. The process is called step and repeat. We do exposure after sequential period. So it's called. So this is the design of the die, and so it is exposed now hundreds of times. Right. just because we can now. So the system is much more complex than just maintaining the optics. It is a mechanic, it's a motorized system which has to step exactly the same distance and reproduce exactly the same way for all of the dyes on the wafer. Not only that, for the second mask now it has to align with all of them and step the exact same distance and do the exact same exposure at every dye at multiple levels. Right? So problem is, so it's a now bigger problem now. Instead of doing just same size, 1x mask, maybe 5 masks in a set, we can easily do them. But now if we have step and repeat, of course we gain on the size. Now we can make 10 micron line and get a 1 micron line, but then repeating it and then repeating the second mask and third mask and fourth mask on all those dyes is an engineering problem. Question?
So step and repeat is possible only in projection printing, right?
Yeah.
But if you're doing contact printing, how will you align the second mask with the?
So before you align, we produce some distance between the mask and wafer.
So it's all done at the same time, like all the masks are put one above the other?
No. So we do exposures with one mask, take it out, develop, do whatever, and put the next mask, put the resist, and now stick in the machine with the second mask. Now we align the second mask with the whatever feature is there from the first mask, expose it again, do yours, whatever, and so those wafers. So all the masks come sequentially after the whole processing over. Right? In contact printing, of course, it's easy to do, but there's contact occurring, which causes the mask to degrade, which causes the resist to peel off. Right? So there are those issues with both, the challenges with both of them. How do we create a mask? So this is before we do any lithography. You have to create a mask. So it's same idea, but here we are doing a pattern generator. Basically translates those solid parts on the design into triangles and squares, which will be written by a beam, right? Because those sizes are depending on how small they are. We use electron beam to write those features in that material on the quartz, what you call quartz plate. So then, depending on if it's 10 times or at same size, we define a reduction, or we define the direct size, direct feature on that, right? So if it is 1x, we don't have to do any reduction in size. Once we do the reduction in time, then again we have either contact printing or proximity or projection printing. Right? So in either case, we have a multiple number of devices, features that are made on that one mask, right? Going back to that I line, G line, and they were basically specific wavelengths of light sources, which we are pushing now towards deep UV, which is 248 and 193, and beyond deep UV is X-ray, right? So we want to push the wavelength down, but once we get to the X-rays, what is the problem with X-rays?
The lenses won't work.
There are very few opaque materials that are opaque for X-rays, because what do? They pass through, right? They pass through human, they pass through bones, they pass through hard material. So it's what do you call it? Optical components will not work. The optical lenses will not work. They will be transparent to X-rays, so they will not they can't be used to control X-rays. Not only that, X-rays and wavelengths beyond that, they destroy optical components because their energy is almost equal or more than the band gap energy of glass. What is band gap energy for glass? What? 8 electron volt. Yes. 8.2 electron volt or 8.1. So we want to push them this side, but we can't go beyond because we then need drastic change in technology, drastic change in the equipment we use for lithography. Right? Right now, what we do is we have an optical source, maybe UV, right, or deep UV, but nevertheless, we can use lenses to focus the light, to adjust the depth of focus to. But if you push it further, we will get a minimum feature size to become smaller, but the whole equipment will have to be then changed. Right? So these are the specific wavelengths that are used in optical lithography. Right? So if you go beyond, they are called next generation lithography. X-ray lithography or other ways are called next generation. They're not called optical lithography. We'll stick to optical lithography here. So these wavelengths tell us the minimum feature size that have been made over decades. So they were projected to go in a straight line, but the sizes have gone smaller. So they have been not just because of the wavelength, but other technologies, other enhancements to the techniques, not only. So they don't just depend on the wavelength of the light now. There are techniques we can do with the mask itself. There are techniques which we can do with the medium for the light propagation that has enabled the feature size to become way smaller than the wavelength itself. So these are just some background that what are the wavelengths and what sizes have been used with those, what minimum feature size can be used with those. Right? And the lamp sources that are used with that. So one usage is to transfer the pattern in underlying layer. The other is to protect, the other use of photoresist is to protect underlying material, especially in case of etching. And in etching, more importantly for what we call high aspect ratio features, HAR features. For that, we need high selectivity. Right? So again, going back to the plots or the tables where we had different etch rates of different materials against different recipes of mixtures of gases and power that we have to know what resist we can use to get some certain depth in silicon or whatever material, whatever wafer we are using. So this is just overview that you are to use this resist as mask for safeguarding this material that is underlying to etch high aspect ratio parts. Left off is another process which we use to define metal patterns. We haven't seen it lift off, or we haven't even talked about how do we deposit metals. But we have to deposit metals nevertheless. To make, where do we use metals? Interconnects, right? So you have devices which are covering a whole area, you have to connect them with each other. You have to do the wiring as we do in macro scale work. Or we have to connect different layers with each other. What do we call those connections? Yeah. So interconnects, and how do we make interconnects? How do I make a line run for certain length and it has certain width? How do we define that line? You have to do lithography again. And in lithography, we define the area where we want metal to stay, right? And we deposit metal everywhere. There's no way to selectively deposit metal only in that region, right? What we do is we cover metal everywhere. How do I get rid of metal from where I don't want it? Because covering the whole thing is just shorting everything. This process is called lift-off. So the idea is that we have resist at places where we don't want it. And red is just showing that actually metal basically makes a film which has this topography to it because there is resist below. Once we expose this to acetone or some chemical which can dissolve resist, we get rid of metal from everywhere where there was resist beneath it. And what we are left with is metal, right? This is just a two-dimensional figure, but basically what we are getting is a metal line made up from there over the whole substrate, right? This is called lift-off. And this is the ideal case where we see such a very well-defined rectangle, but actually there is always this overhang left behind. There are different ways how do we get rid of that. So these are called this on the metal line, some material, some metal which is left because of this guy, call these overhangs. We do ultrasonication to get rid of that. What is ultrasonication? There was a question in the chat. Ultrasonication. Cavitation. Cavitation is what's cavitation effect? I know it first and I've served in submarines. Cavitation. What is cavitation?
Creating a bubble in fluid.
Creating bubbles which burst very quickly. When they do that, what do they result in? Noise, and they have this localized bursting effect. Localized destruction of those bubbles results into the cleaning what we do for our case. But here, so ultrasonication results into the removal of the loosely bound material, right? They just remove those. So cavitation is creation of tiny bubbles and their breaking, which is a vigorous process. So that vigorous process results into the localized cleaning. That's what we do to get rid of overhang. Or we do something else which is called chlorobenzene dip. I think I have a slide on that somewhere. We'll look at that. Chlorobenzene. So chlorobenzene basically makes the top layer of resist hard. Right? So once we do that, it has some resist which is hanging out, which wouldn't let this metal to be deposited at that edges. Well, I think I have a slide on that later on. So now we have probably seen discussed many things of properties of resist. So what are physical and chemical properties of resist that are important for us? So end result is we want it to have high resolution and we want it to be sensitive, right? What do we mean by resolution? Who bought a new TV? Anybody's looked at those LCD TVs lately? How do they define their parameters?
How many pixels they have?
Pixels, right? Resolution. What are the numbers they use? 720p, 1080i, right? What do those numbers mean? I haven't heard from you ever. I don't hear from you ever.
Pixel size.
So how many pixels they have crammed into that space, into that whatever, right? So that defines resolution, right? So we want a resist that can have high resolution. Now for that pixel, what is important for a pixel in terms of, I can cram many of them, but what good are those if I can't distinguish one from the other, right? So they have to be distinguishable from each other. So they're not just how many, their size also. So if we have many more pixels, we get a sharper image, which means maybe a white line will have less number of squares in it, right? You can have many more. Similarly, for photoresist, when I say want it to be high resolution, it means wherever I make a design, it has to have a steep edge at that design. Let me draw it. I've drawn it here also. So the idea is that, is this high resolution or this guy is high resolution? Do you think the upper one is high resolution or the lower one is high resolution? Upper one, because the lower one is, if I put few of those close by, it will be hard for me to distinguish one from the other, one trench from the other, one feature from the other. But in this case, this PR is very high resolution. I can put many more of these features very close by, and I can have them very small. Does it make sense? So it's not always the feature size that needs to be small, it's how often can I repeat them, right? So in a given picture, can I have image which is very sharp, which basically translates to how small are the pixels, right? So we want it to have high resolution. Sensitivity. When we expose the light, we want the resist to change its chemical features, right exactly where the light strikes, and not where it doesn't strike. Because this occurs when there is internal reflection of light, right? So this is less sensitive than this guy. This is more sensitive. It's changing property only where the light reached the resist. But in this case, it's less sensitive here. It's making the feature size to be bigger. Index of refraction again results into the internal reflection of resist, which will cause the end feature to be bigger than what we actually you were exposing it. Right? So then these are all physical properties. Has to have high viscosity, low viscosity, depends on the application. Because viscosity will define how thin of resist can I put on, or it will define how thick of resist I want on a surface. Especially for MEMS, where people make high aspect ratio features, they want something high viscosity, right? So they have thicker resist layer. Etch resistance again, going back to how much of it gets etched given a one recipe. Thermal stability, flow, it's all interconnected to each other. Ambient shelf life, which translates into how long can we keep it, right? If I buy resist for $2,000 and it's good for 2 months, and I may not be able to use the whole gallon because all we use in one exposure is 1 squid of pipette, which is 2 ml at the max, right? So using 2 milliliter of a gallon, it's going to take months before I finish it. So if it expires in 2 months, I lose that. So from industry point of view, these are some of the things which are important. Toxicity, which is one of the reasons why negative resists have been phased out. They were carcinogenic. So they were a affecting the users, the engineers.
What is process strategy?
How much do we have room in a processing? So if I'm supposed to do soft bake at 90 degree and my equipment give me 88 degree, would that be still workable or not? Or my equipment gives 92 degrees Celsius. So latitude in the process conditions, would they be still good enough for that resist? So the more stringent, so it's basically how much play we have in any process at any step. The more stringent it is, there are more chances for failure of the process. Right? Does that make sense? If I have plus minus 5 and I have plus minus 2, which one would you prefer?
So it's the tolerance value.
It's the tolerance on the process. Either side, how much can we go during the different steps of the process. And temperature of glassification, of course. So what do we need ideally in a resist? Want high sensitivity, high contrast, high resolution, high purity, long shelf life, minimal and non-toxic solvents used for that, high glass transition temperature. So during the low temperature process, it doesn't change once I've done the classification. Easy handling, low cost, but it doesn't exist in ideal resist. So there's always trade-off. There's always trade-off on what we want to achieve. Questions? We'll get into resist chemistry. Of course, there is the three parts to it. One is what keeps it liquid, one is what is chemically active, and one is what keeps it, what gives us mechanical properties. Resin, pack, and solvent. So pack is, in positive cases, it's an inhibitor in unexposed regions. It inhibits the reaction in unexposed regions. So you'll see this DNQ Novolec over and over. It's nothing but short for resin called Novolec and a pack called this. Right? So Novolec pack is a type of resist. Right? So solvent is what gives it a liquid state until we get there. But once we spin it and bake it, there's some of that left behind, but it's less than 5%. We can still live with it. We get rid of that once we do baking. Once we do hard bake, then we get rid of all solvent. Right? But we need some solvent during the what is called expose it and development. We need some solvent during development. So we don't do hard bake before that. So in Novolec, there are hydrocarbon rings with 2 methyl groups and 1 OH, long chain polymer. And DNQ is insoluble until it's exposed. And once it's exposed, it results into a carboxylic acid. And that is then developed in developer. Right? So DNQ is what keeps the resist insoluble in unexposed regions, soluble in exposed regions. Make sense? Positive resist. So this is just reaction for that. So these were well for I line and above, but since we are shrinking down the size, we are getting the wavelength to become smaller, we are amplifying the reaction as well. Let me ask you something. Common sense. High, smaller wavelength travels faster or shorter, or larger wavelength, or not faster. Shorter wavelengths travel longer, or longer wavelengths travel longer.
And what medium? Shorter.
Any X medium.
Shorter.
Shorter wavelengths travel
Longer wavelength travels longer. between medium and space, it's all the same.
Longer wavelengths, we have two school of thoughts. One says shorter wavelengths travel longer, one says longer wavelengths travel longer.
There is always some attenuation in the medium, so it depends on how much energy my wavelength carries. So
Same energy, wavelengths.
If you think about it, if you have an ultrasound, you can't go very deep with a high frequency ultrasound probe. But the bass from the car on the street you'll hear, even if it's true.
So he's leaning towards longer wavelength travels further, right?
Yes.
You said shorter wavelengths travel further.
Shorter wavelength contains it actually relates with energy, like shorter wavelength with the same shorter wavelength has more frequency, right?
Shorter wavelength has more frequency, so
This is
wavelength frequency are
inversely-
just inverse of each other.
Inversely proportional to frequency.
So shorter wavelength is
Inversely proportional to frequency. So it can move faster, you can travel more.
so
Shorter wavelengths lose energy quicker. So, I mean, the light is energy after all. So, in order for the energy to transmit from point A to point B, it will transmit with, what do I call it, more, I mean, you'll have more energy transmitted if the wavelength is longer.
yeah, so you just have to get the signal across. So energy is yours, but given ideal
Like
conditions,
simple microwave, like anything heated in a microwave cools down very quickly because microwaves, the wavelengths
but
are short.
standing right there, do I get microwave reach
No,
me?
that of course not.
So it doesn't travel even that further.
Exactly.
But wouldn't the left wing of the class more closer to that?
Well, microwaves reach you just fine without gravity shielding. Your phone works, right?
Right. So it's a but your phone goes out of range very quickly. You are just maybe even a few hundred yards away from the footprint, right? So see the footprint of those towers also. They are very small. Right? So yeah, this part of the question is misleading. It's given the complete freedom on the aerial length. If I can make my aerial to be as long, I would prefer long wave because that's the only impeding factor. We need to keep. You want to use short wave because we don't need then longer antennas on the other side. So I can listen to BBC on short wave all over the world. I guess everybody knows BBC except maybe, or maybe you know as well. So, but longer wavelengths travel further. The only impediment is we need longer antenna to receive them. I know that again from my experience in submarines. So they have this, for the transmission around the world is very, very long wavelengths. If they have advantage, they can reel the antenna out in the water to receive those. So we are reducing our wavelength. Our penetration is reducing. Right? So we do chemical amplification. To chemical amplification, they use what we call photoacid generators, which is a catalyst for reaction in photo-enhanced. What is PEB? PEB is written somewhere. Oh, post-exposure wake. That's post-exposure wake. So what we have is we have light they direct, but once we do the wake, they result into the reaction that makes that chemically changes the resist, which will become then soluble in developer. But they are then more sensitive to contamination because they are chemically ready for reaction. Alright, so how do we define resolution? It's the ability to print minimum size images under allowable variation tolerance, right? Under allowable tolerance. What defines the resolution wavelengths and hardware? So lambda is not the lower limit. We can go smaller than lambda. Right? So if you remember that plot, it was coming linear, but then it has fell down the wavelength that we use, because we use other techniques now to get smaller feature size than the lambda itself. Generally, we would say we cannot define a feature which is smaller than lambda, but because we are using techniques apart from just the wavelength, which gives us ability to produce features smaller than lambda. Does this line make sense? That lambda is not the minimum feature size. We can make features smaller than lambda, but there are other issues which come into play, which makes it hard to scale down the resolution. And hardware is diffraction, lens issues, mechanical stability. So these are totally. So one is an optical issue, the other is more of a system issue.
The numerical aperture does not affect.
Can we change numerical aperture? So there's limited things we can do with numerical aperture.
So that forms the lower limit of the.
That's also one of the factors in there. Can we change numerical aperture?
Without changing
That's
materials itself.
to the extent that you can change your optics and your index of refraction of your medium.
You cannot change. You cannot use this topic because this has been already picked up by someone. But yes, you can change medium by using what we call immersion lithography, by using liquid as the medium for the propagation of light. And in liquid, you can change numerical aperture, right? So it's all what you call Bragg's diffraction limits, right? So those you can change with that. And optical properties of resist, contrast, sensitivity, again, those concepts, how steep your walls can be, and then the physical properties that resist can swell, make features small, make feature different, can have variation in the features that we get at the end of the process. Process characteristics, splits, bakes, all those processes can have variation. Even in an oven, you preheat some temperature outside, but within the oven there can be variations in temperature. Even just a couple of degrees can have problems with how your bake occurs. One thing here, there's a big thing which is called what do you call that? Humidity. Humidity is one big process variable. If you are too humid, your process will just restrict. You won't get any exposure. So your resist can have problems if there's high or low excuse me, humidity. Okay, so how do we define contrast? Probably you can stop here because this needs much more detailed discussion. Excuse me. Any questions? So, excuse me. It says, welcome to Texas. Any questions? Yes. We'll stop here. The homework is due on Thursday. I'll change the deadline in Blackboard. Yeah.
I have a question on term paper. So, do we need to suggest a new idea and prove out the idea?
Yeah.
How can we prove that?
Can use theory, can use conjecture, you can use logic from somewhere else where they might have used it. Just like this immersion lithography. You can ask some questions, what process can be improved, what parameter can be changed with something else. So you have to read up on that.
Do we have to do it on the 20th?
You have to, 20th is the deadline. See, you have to, you can start discussions now. Send me something if you want my opinion or some feedback.
Can, could we postpone it to?
Probably we
Because there
don't
is
have
a-
much time left behind if we keep on postponing them.
Because just that there is, I was heard there's a power outage on the 16th in the library and the databases are not available on that day.
So just 16th is the issue, you can do, add one more day
Yeah,
to the
but I
deadline.
just didn't want to take that chance.
It would be great if we could have maybe another week
Yeah.
on the paper.
But then we become delayed on the later deadlines. There are other things that have to be done. Let me think about it. Send me what structure you want to suggest, and let me take a look at the
Yeah,
schedule.
if I week 27th.
I'll have to see this, what I have scheduled with me for the class presentation and all that, so I'll have to take a look at it.
So class presentations on the same day or that would be?
No. When you turn in your deadline, then I'll go through it and give you some feedback before your presentations are scheduled. So on your write-up, I'll give you some feedback to improve on your final presentation in the class.
So
And
that-
then,
So that's not the final thing that we are submitting.
if you want to finalize it like that, I'm fine. But generally, I give some feedback to improve on that, so you can improve your grade on that.
Oh, so
So
we
there'll
can make
be a
changes on
class-
it and then we can, the final term paper we'll submit at the.
No, that final would be your class presentation.
Yeah, that's so. We'll be submitting the paper again on that day?
No. But you'll be presenting after that, giving you feedback.
Okay.
So you have to now cater for what you have been told to correct.
Okay.
Right? So your deadline, let me see if there is room for flexibility or not. Maybe there is not, I don't know. Have to see the schedules. Right?